Okay. Welcome everybody to the first seminar of the year. This is the seminar of the Latin American Network on Electromagnetic Effects in Strongly Interacting Matter. And I'm glad to have as the first speaker of this year, Kirill Tuchin. I hope I have pronounced well your name, from Iowa State University. So let me just first give a brief introduction of him. So Kirill did his bachelor, master, and PhD in the Tel Aviv University, master and PhD in theoretical physics. He was a postdoc at the INT, the University of Washington, and at Brookhaven National Laboratory. And he was a fellow at Riken BNL, again in Brookhaven. He was assistant professor at the Iowa State from 2005 to 2010, and he became an associate professor in the same university in 2010. And from 2015 to current times, he's a professor in the Department of Physics and Astronomy at Iowa State University. I think everybody here knows him. So he has several awards and honors. As a fellow at Riken BNL, Research Excellence Award in the School of Physics and Astronomy in the Tel Aviv University. He got 3 times the award of the most valuable classroom instructor in the university where he teaches. And he's been, since many years ago, working on the topics that are the main interest of this network. So please, Kirill, thank you very much for accepting the invitation. The microphone is yours.
Well, thank you, Anna, for such a nice and kind introduction. It's a privilege to be first on this series of seminars. I'll try to give a very general, description of what we are doing. I may go into details, but please stop me if you think that there are too many details, or if not enough details, also tell me. In other words, since this is a seminar, please feel free to stop me anytime and ask questions. And actually, I'll enjoy the interaction if you have any questions. So the subject I am going to talk about today is the magnetic field and rotation, right? And the magnetic fields I would like to talk about are very strong, and rotation is very fast. And now, before we proceed and actually talk about the interplay of these two phenomena, let's first look at the general scales about which we are talking about. So magnetic fields, I'm sure you've seen this many times before. I'm not sure even who first started this as kind of chart, but the magnetic field on the left-hand side, the scale is in Gauss. And you can also see the various examples of this magnetic field, started from the human brain, which is a very small field, 10 to minus 11 Gauss, and all the way to neutron stars. You have 10 to 12, 13 Gauss. Then at a scale of about 10 to 13 power, the nonlinear QED starts, meaning that the Maxwell equations become nonlinear due to the quantum corrections. And then above that, there are magnetars, neutron stars with a strong magnetic field. And even above that, the heavy ion collisions that produce magnetic fields, which are strongest in the nature. The only exception, the only stronger field might have existed in the early universe, but those, of course, we cannot measure. But the magnetic fields in heavy ion collisions are, in principle at least, accessible for observations. And this drives much of the research in the strong magnetic fields these days. Okay, so this is a very brief kind of summary of this magnetic field heavy ion collisions. You take two heavy ions with charges Ze. E is electron charge, and Z is number of protons. And you collide these two off center, and this produces some strongly interacting matter, but also produces a very strong electromagnetic field, just because these two nuclei carry electric charge, and they're also relativistic. And if you compute this magnetic field, you'll find that if you neglect the effect of medium, plasma, for example, then you have this blue line shown in this figure. It's a very strong field, but decays very fast. If you take into account the effect of plasma, in particular the conductivity of this plasma, then this receding the nuclei induce electromagnetic field in plasma itself, and this field becomes dominant very quickly. And you can see this red line, the red curve, showing that the field in plasma is much stronger than in a vacuum. Why this happens? Well, the very simple model can explain this. So if you take the response of the medium and expand near the small frequencies, it looks like this. It's a general formula. Sigma is conductivity, and omega naught is a certain typical frequency of the electromagnetic field in the medium, right? And so if you look at it, the system from the laboratory frame, right, then there is a relativistic effect of time dilation. And so the medium response time is not 1 over sigma, but 1 over sigma divided by the Lorentz gamma. And so this gamma emerges in the numerator and makes the response very strong, even though the conductivity, the electrical conductivity of the medium is small. And this explains the strong effect of enhancement of the field. And this makes it possible for observation, even though it's very difficult in practice to track the effect of the field itself. Okay, so my student Evan Stewart, who recently graduated, and I done a lot of work on this, and this is basically our two papers in which we not only computed this electromagnetic field, but imposed the correct boundary conditions, initial conditions. In other words, we considered these two colliding heavy ions before the collision, computed the electromagnetic field just before the collision, which is in the vacuum. And then when the plasma emerged, then we solved the Maxwell equations in the expanding plasma. And you can find the details in those papers. Okay. Now let's talk about rotation. Rotation is a novel subject, I would say, as far as the heavy ion collisions are concerned. Let's start from the Earth. Now, on this axis, on the vertical axis, is angular velocity of rotation. So the Earth rotates with 10 to minus 4 revolutions per second. Right? You can easily compute that. Then neutron stars is, of course, can rotate much faster, but the dental drill rotates even faster. Actually, I found it amusing that the fastest rotating macroscopic system on Earth is the dental drill. And if you think about it, it's good to know that it's so fast. And so then there was a recent report that a trapped silica nanoparticle can be rotate with 10 to 9 revolutions per second, which is amazing achievement. So what they do, they take a laser pulse and shine on this nanoparticle, and this laser pulse makes it rotate with this huge angular velocity. And then there is a huge gap, right? You can see this huge gap, and I put in a question mark because I don't know, I don't have any examples of what happens here, any systems that rotate with so large angular velocity, all the way to heavy ion collisions, in which we know now that the plasma, quark-gluon plasma, rotates very rapidly. And you can see this on the right, the recent computation by Dan and Juan of the vorticity of quark-gluon plasma, and these numbers here on the vertical side is rotations, units per Fermi. How many revolutions happens per Fermi? If you translate it per second, this is the number here, and you can see this is by far the fastest rotating system in the universe. Okay, so then the question arises: so what is how do you combine the heavy ion collisions, the rotation and magnetic field together to see the interplay, right? Okay, so this table that we prepared for our upcoming publication talks about various systems and their corresponding magnetic fields and angular velocity of rotation. Another quantity that is relevant here is the synchrotron frequency, which is essentially the electric charge times magnetic field times speed of light over the energy of the particle rotating in magnetic field, right? So both magnetic field and rotation are kind of rotating motions, right? So electric charge in magnetic field rotates on a circle. So it's meaningful to compare the synchrotron frequency, the frequency of rotation of electric charge in magnetic field, with the frequency of fluid rotation, in which charge is embedded, right? So in Earth, for example, you take magnetic field, it's 10 to minus 5 electron volts squared. I converted everything into electron volts so we can compare. And this translates into this 10 to minus 6 over the energy of a particle measured in electron volt. The corresponding angular velocity of rotation is many, many, many orders of magnitude smaller, right? So no matter what kind of energy you take, you still be, the synchrotron frequency is still much larger than the angular velocity of rotation, unless you really go to the extreme and take the cosmic rays and take the most energetic particles in the cosmic ray spectrum, such as 10 to minus 1 electron volt, then you can compete with the angular velocity of rotation. So only the fastest particles may feel the effect of rotation of Earth. Okay? So rotation of Earth is not the best place to look for the effects of rotation and magnetic field. So let's skip all the way down to quark-gluon plasma. And there you see that the synchrotron frequency, if you plug in typical numbers for magnetic field, is given there, 10 to 12, 10 to 16 electron volt, while the angular velocity of rotation, the vorticity is 10 to 9, right? So if you take for the energy of the particle is say GeV or something like that, or 200 MeVs as a temperature, right? Then you can see that these two numbers are comparable. So the quark-gluon plasma turns out to be also very special in the sense that you can see the effect of rotation and effect of magnetic field in the same system. And this is what we're kind of interested to study. So this is, shows you why the plasma rotates, right? Because the collision of the two heavy ions is off center, and therefore there's huge angular momentum that is transferred, partially transferred into the quark-gluon plasma. It makes the plasma rotate in the plane so that the angular velocity is perpendicular to the reaction plane, and it's more or less coincides with the direction of magnetic field. So what we want to study is a system that rotates around the same axis as the external magnetic field. Okay, so this is a summary of what I just mentioned. We have heavy ion collisions. On the x-axis is the energy of the collision. On the y-axis is angular velocity, either of rotation or its synchrotron frequency. And you can see that the synchrotron frequency is increasing with energy, just because the magnetic field increases proportionally to the energy of the collision. while the vorticity decreases with energy. And so there is some point, at some point they cross each other, which happens. It's difficult to say because it's a rough estimation, but somewhere, in this region, in the region called 2, somewhere there is a crossover between the two lines. And so to the right, in the green line, you have what we can call slow rotation, and in the region 1 is rapid rotation. Right. So
sorry, Kirill.
yes.
A question: neutron stars in this case are in the region 2, or where can you locate it, for example?
Well, in the region, yeah. So for neutron star, let's go back to neutron star. The magnetic field you can see is the largest is 10 to 14 electron volt squared, right? If you convert it to the synchrotron frequencies, 10 to 13 over the energy, while the angular velocity of rotation, is tiny, 10 to minus 12.
Okay, I see.
If you take a matter, if you take a neutron star matter, it won't feel any effect of rotation. But wait, okay, I have something to say about it later. At first, it looks like it's two scales completely, different, and if you put for the E the temperature of the star, you'll never get these two numbers comparable. I mean, the synchrotron frequency is always much, much, much larger than the angular velocity of rotation. But as I said, let's wait. And something unusual to say later, okay, about this. So at first sight, there is no effect. Okay, so this is my team that for a lot of already results, some of them are published. So Matteo is our postdoc, and Nandagopal and JD are my graduate students. And if you want to read a little bit more details about this, it's in these two papers. But what I will show you is way more than you can find on the web right now. Okay, so let's set up the problem first. I want to study rotation of a particle, and I would like to study how this particle emits electromagnetic radiation eventually, because I know that the radiation will know about the trajectory of the particle in this system, so it will know about both the magnetic field and the rotation of the system as a whole. Okay, so to study this, I need to know, classically speaking, the trajectory of the particle. And then later we'll talk about the quantum mechanics. So how do I do this? Well, the straightforward way of doing this is going to the rotating frame. And in the rotating frame, the equation of motion of a particle in magnetic field is given in this equation. And you can immediately see that there is a centrifugal force. We know this from undergraduate physics. There is centrifugal force. And this centrifugal force will push particle to infinity. Okay? This is not our system, right? We're looking into plasma rotating and intact, not spreading around very rapidly. So therefore, what we need to do is to actually consider some kind of a mug, right? So we want to put a particle or element of volume into this mug, and I would like to fix its trajectory. I want to force this particle to be inside the mug. Meaning that if I go to the rotating frame that rotates together with this particle, the particle is going to be at rest if I neglect the Lorentz force. If not for the Lorentz force, the particle is at rest in the rotating frame. Right? Now I add the Lorentz force, and the particle starts to rotate around the direction of the magnetic field. And then I go from there to the stationary frame and look at the trajectory of this particle, its motion, from the point of view of an observer in the laboratory frame, which is stationary. So this is exactly what I do here. I start from a particle rotating on a circular trajectory around the direction of the magnetic field. So R and V are some parameters, a position and velocity in the rotating frame, and then go into the stationary frame. So omega here, the capital omega, is the angular velocity of rotation of this fluid in the mug, right, the plasma, and little omega is the synchrotron frequency. Okay? And this is illustrated for the classical particle in this picture, right? So you have a particle performing 2 circle rotations with different frequencies. Okay. So then going forward with this classical model, you can compute the total intensity of the radiation according to the well-known formula. If you know the trajectory, you know the intensity W, then I averaged it over the period and got some long but after all simple formula. If you take now the no rotation limit, we get back to the usual formula for the intensity of the classical particle radiation. Notice that it's proportional to the energy squared. And then conventionally, when people talk about this quantity, they take the ratio of the total radiation to the one in the classical limit, the no rotation limit, I'm sorry. And this is what you get. The black line is no rotation, so it's 1. If you include rotation, then it depends whether rotation is in the direction of magnetic field, meaning it's omega is positive, or in opposite direction. If it's in the direction of magnetic field, then there is strong enhancement. And if it's in the opposite direction, it's strong suppression of the radiation. Right. Now, you should take these results with a grain of salt, because the classical calculation neglects the recoil, meaning that we assume that the radiating particle is always have the same energy E, which is not true, because see, the amount of the energy radiated grows as E squared. Right. So therefore, very soon the energy is radiated, the particle radiates so much energy that we cannot neglect the recoil, and this is actually happens pretty early here. This is the dashed line. And so you can see that there are 3 lines. So the effect of the rotation is to either enhance or suppress the radiation. But you can't go too far with this conclusion, because this classical model simply fails. But it gives us kind of an idea of what's going on. Now, before going into quantum mechanics, let me make a very important remark here. When you go into rotating frame, then your metric looks like this, and you notice that this quantity in front of dt squared must be always positive to make sense, right? And it tells you that the distances in your space-time, in your rotating metric, cannot exceed 1 over omega. Right? You can think about this as a wall of the mug. So this is absolute limit to where you can extend your system. That can be a problem. It's not easy to take this boundary into account. I will talk about this later in more detail, but to begin with, we'll consider a system in which magnetic field is so strong that the magnetic length, this quantity here, is much shorter than 1 over omega. In other words, the magnetic length is so short that I can simply disregard the effect of the boundary. Right? Everything, all the dynamical processes in the system happen at the distances much smaller than the size of this white cylinder, where this inequality becomes really important. And we refer to this as slow rotation. We have had some trouble with the referees because the slow rotation is actually not slow. Because as you've seen before, for example, in the neutron stars, this square root of EB is a huge number compared to the omega. So in fact, this is all physical systems we know very well satisfy this condition, except quark-gluon plasma, which satisfy this condition only at very high energies, which I'm going to talk about them right now. Okay, so the slow rotation is again the situation in which the size of the white cylinder is not important, and it applies to almost all physical phenomena. And the rotation actually is not necessarily slow in the absolute on the absolute scale. It's only slow compared to the synchrotron frequency. Okay, now we can go to the Dirac equation and do everything I just showed you in quantum mechanics. So we take the Dirac equation in a stationary frame, rotate it to the, take it in the rotating frame, and then we transform into the stationary frame by doing a rotation with angular velocity minus omega. And so this is the Dirac equation. This is the effect of rotation is included in this gamma mu because it's kind of curved. It's cylindrical coordinates, right? We choose the symmetric gauge, which turns out to be the most simple in this problem. Compute the Christoffel symbols, and then we can represent the Dirac equation as in the Schrödinger form, right? With the Hamiltonian given by this equation. So it's interesting that the effect of rotation is completely included in this one term here, omega dot j. So j is total angular momentum, and the effect of magnetic field is included in this term minus qa as usual. It's very interesting that all this complicated transformation from the rotating frame into the stationary frame produces only one simple term here. And it's exactly the same as in classical mechanics. Okay, so P is the usual operator of momentum, and Jz is total angular momentum operator. So then we'll look for the solution to the Dirac equation in this form, in the cylindrical coordinates. So E here, capital E is energy, epsilon is plus minus 1 for particles and antiparticles. Pz is projection momentum of our particle on the z-axis. M is magnetic quantum number. Phi is azimuthal angle. And these functions, F1, F2, F3, F4, are the functions of the radial coordinate. So this rho here is actually dimensionless quantity proportional to r squared. R is the distance from the axis of rotation. The solutions depend on the sign of the magnetic field. Or to be more precise, it depends on the product of this on the sign of the product of the charge and magnetic field. In other words, if you flip the magnetic field direction and the value of the charge, plus to minus, you get the same exactly physical situation. Right? So these functions f1, 2, 3, and 4 are all different, and they satisfy they satisfy similar equation but with different coefficients, so-called Comer equation shown here. I will not bore you with all the details unless you stop me. And you solve this Comer equation and obtain usually, as usual, the form of this functions u. And if you know u, this is the same as f. Okay, now we have to set the boundary condition. There are two boundary conditions. One at the origin. Okay, so we have to ensure that the solution to this equation is finite at the origin. Okay? And this is done by choosing the hypergeometric function 1f1, and I think it's a confluent hypergeometric function. And second boundary condition is imposed at the end of the white cylinder, which is 1 over omega. But since we assume that the rotation is slow, we can actually assume that omega is close to 0 and r is infinite. So we set the boundary condition at infinity, which means that we require that at infinity, in the radial direction, these functions u vanish. And this is precisely the procedure is done if you have only magnetic field without rotation. As the result of this boundary condition, we get this function, this hypergeometric function becomes a polynomial. And these functions and these coefficients as must be positive integers. So this is a quantization condition. And so
Right,
this
Kirill?
one, yes.
This solution is unique?
Yes, this solution is unique, yes.
Okay.
Yes. Right. So, so general solution consists of two hypergeometric functions. One of them is increasing at infinity, one of them increasing at 0. And so the boundary conditions eliminate one of the first boundary condition eliminates one of the hypergeometric functions, and another one finds a value of a region, certain values of these parameters A, in which the hypergeometric function is vanishing all at infinity, far away from the axis, the rotation axis. So this requires then that this lambda becomes integer, shown here, and gives us the dispersion relation, the spectrum of the fermions in the magnetic field, including rotation. So M again, M here is magnetic quantum number, and capital M is the mass of the particle. Usually I'll put it M to 1, this capital M to 1, just so that it's not confuses us. Instead of this AS, which is different for different components of this bispinner, it's convenient to introduce one number, a radial quantum number, we call it A. So finally, this is how the solution to the Dirac equation shows up. It depends on 4 quantum numbers. So N is the principal quantum number, A is the radial, Pz is momentum along the z-axis, and zeta I'll explain on the next slide. Now L here is the normalization factor. Essentially, L is size of the system in the longitudinal direction along the z-axis. It will disappear from the final formulas. These functions I are related to the Laguerre functions, and L here are Laguerre polynomials. So all these expressions are familiar from, I think, 1960s or 70s, something like that. The function, the coefficients C are related by one relationship here, but otherwise they're free. So we'll choose those coefficients C to satisfy some other constraints. But before we do that, we need to check that our approximation, this low rotation approximation, is satisfied. So we'll take R in compute expectation value, or R squared, or R cubed, any power of R, and make sure that this expression, for example, R squared average, is much smaller than 1 over omega squared. This is our assumption that the system is always constrained to be far away from the boundary. And if we can compute this R squared explicitly and make sure that it's much smaller than 1 over omega squared, which requires that the quantum numbers N and A be smaller than this ratio, QB over omega squared. And since we assume that omega is small and QB is large, then it looks like it's this M causality is a very large number. Okay. So this is the only thing that we have to check when we make a computation, that we never approach this large number. Otherwise, if we're sensitive to this number, then it means that our calculation is not so good. Okay, so we can fix the remaining quantum number, I call it zeta, by requiring that our functions, our solutions, be eigenfunctions of the helicity operator or a spin magnetic moment mu, which is related to the canonical spin tensor. So in practice, we choose the second option, which is just more convenient in our calculations, but it actually doesn't matter. You can choose either one of them to specify the coefficient C, right? So this coefficient C here can be set, any way you want. It will satisfy the Dirac equation. Okay, now we're going to the photon wave function. Since remember, I want to compute the synchrotron radiation spectrum, and for the photon wave functions can be chosen any way you want. actually the original computation was done with plane waves, but it's more convenient, I think, more natural to use the cylindrical waves since we're using the cylindrical coordinates. And so what you do, you solve the free, the equation, wave equation, and expand its solution in terms of these functions S, T, and P, the scalar, toroidal, and poloidal functions. Again, if you like to doing it in using the plane wave, you can do this. It doesn't matter. So these functions T and P are also well known since the paper of Chandrasekhar and Kendall many years ago. And so what you do then is we normalize this properly and so on, and then our cylindrical waves look like this. Okay, this phi is a vector. Phi depends on the helicity, plus or minus, right or left. The L is an azimuthal quantum number. K perp is a quantum number in the radial direction, momentum in the radial direction, and Kz is momentum in the z direction. Okay, and omega is this omega is energy of the photon. Now it's important that in our calculation we assume that photon does not interact with the medium. So the fermions and plasma rotate, right? But the photons they emit are completely they escape the plasma. I don't see it at all, which is a nice first approximation. If you're talking about the covalent plasma, the interaction of photons with it is very small, and so therefore we do not take into account any effect of plasma on this photon wave functions. Okay, so now we proceed to the emission rate, as we taught in quantum field theory. Start with the S matrix. So this is final fermion state, initial fermion state, and the photon wave function. Now we denote the final state quantum numbers by primes. So whenever you see prime, it means the final quantum numbers. And so the rate is obtained by taking absolute value squared of this S matrix, multiplying by energy of the photon, integrating over the phase space, and all the stuff to get the intensity. Okay, this is the formula where J dot phi is the matrix element describing the transition of an initial electron into the final state, or final into the initial. Initial to the final, of course, and emitting the photon. It's a complicated expression. I didn't show it here, but the type of the integrals that appear there are shown here. So it's a Bessel function and two functions involving Laguerre polynomials, which can be computed, fortunately, using this identity here. And finally, we arrive at some long expression, which again, I'm not showing here. You can look at in these papers. The expression for the intensity as a function of the initial energy of emitting particle and magnetic field and so on. Now, obviously, not all energies of photons are allowed to be emitted. When a photon with given energy E transfers to energy E prime, it emits a photon with energy omega, but this energy E in E prime are discrete. Right? Therefore, there's only a discrete number of photon energies allowed to be emitted from such a system. And this can be computed using the usual conservation laws. So energy and momentum conservation. So we'll choose a reference frame in which momentum of the emitting fermion is 0. We can always do boost such a frame and solve the conservation laws. So the first one is conservation of longitudinal momentum. Omega naught is the solution to this conservation law problem. And you can see that this omega naught, the frequency of the emitted photon, is a function of initial energy of the emitting electron, angle of radiation with respect to the magnetic field, theta. This parameter B depends on the omega of the angular velocity of rotation and depends on the difference between the m and m prime. So magnetic quantum number of initial and the final fermion, which is the same as the angular momentum of photon. And yeah, so then you can average over whatever quantum numbers of the initial particle you would like to obtain something, some simple expression. I'll show you the spectrum. Okay, so this is the spectrum, the intensity of emitted radiation per unit of as a function of the photon frequency. Omega is the photon frequency. So the dashed lines is the spectrum without any rotation. It's usual synchronous radiation spectrum, right? You can see the dashed lines, clearly single lines. But if you take into account the rotation, then this one line, first of all, splits into many lines. And the splitting is caused by the fact that now energy depends also on magnetic quantum number. Right? We know that if omega equals to 0, if there is no rotation, there is no dependence of energy on magnetic quantum number. But because of rotation, there is a dependence, and you see these many peaks corresponding to different magnetic quantum numbers. We also notice that the entire spectrum shifts to the left, to lower photon energies, and down, right? So the intensity becomes smaller. Okay. And this is corresponds, well, in this figure, the angular frequency is minus 0.01, meaning that the rotation is opposite to the direction of magnetic field, which is 0.1 in units of fermion mass. Okay. Now, if you would like to look into the more details of this expression, you can look on the dependence of intensity on the final quantum numbers, say radial quantum number of final fermion, A prime, and you can see that the radiation, the intensity is concentrated in a very narrow range of these A primes. What we want to do now is to sum over all A primes, all N primes, to find the total intensity of radiation, right? We want to like to know how much total radiation is emitted by plasma. But forget about plasma for now. I want to compute how much individual particle radiates. Okay, one fermion, how much it radiates, given its energy E, and given the magnetic field, how much radiation is emitted. And to do that, I need to sum up over all final quantum numbers. So A prime, fortunately, is concentrated in a pretty narrow region of values. Okay. You can look at this in this figure. This is the intensity of radiation versus A prime, the radial quantum number of the final fermion. Right? This is for A equals to 1, the quantum number, the radial quantum number of the initial fermion is 1. And the final one, A prime, can be anything. Right? And you see that as you go up in the quantum number N prime, the principal quantum number of fermion, the intensity here on the y-axis, right? The intensity of the radiation becomes very, very small. Look at this, it's 10 to minus 28. So you pretty much can neglect all these contributions except those few, this one and that one. Okay, and you see that this happens at A prime very close to the initial A. So these observations help us actually to perform the numerical computation, because otherwise it's really tremendous computation. But if you notice where the main contribution coming from, the computation is much easy to do. And then in addition to the summation of all the quantum numbers, you need to integrate over the final angle of the photon radiation. And again, fortunately, if the energy is high enough, all the radiation is concentrated in the plane perpendicular to the magnetic field and perpendicular to the direction of rotation. And here also you see the effect that we already mentioned before, that black line is no rotation. So if you have rotation in the direction of magnetic field, you have enhancement of radiation. And if the rotation in the opposite direction, you have suppression. We've seen this already in the classical formula, but now we can start to see this in the quantum computation as well. Okay, let me skip that. Now, to compare our results, which I'm going to show in a second, what usually is done is taking the intensity divided by the classical limit. This is the formula I've shown you before. This is classical limit. Another way to kind of see whether our computation is correct is to compare it to the quasi-classical formula. Right? You can find in the many textbooks on the quantum field theory that you can compute the intensity of the synchrotron radiation using the quasi-classical approximation. And this is the formula. This formula is true if energy is high enough. And this is what we're going to compare with. So now I'm showing you the intensity, total intensity of the synchrotron radiation that we computed. So let's start with omega equals to 0. So the dashed line is the quasi-classical approximation. On the y-axis is the ratio of the total intensity per the classical intensity. Okay, so intensity divided by E squared, essentially. Now the x-axis is energy of the emitting particle. So the dashed line here is the quasi-classical approximation. And this line here, you can see, you can see this line here approaching our computation for the no rotation, approaching this dashed line. So there is agreement between our computation and the known results, quasi-classical results, in the limit of no rotation. Then let's take rotation into account. You see that, say, when omega is 10 to minus 6, plus or minus, you have divergence of these curves from the omega equals to 0 curve. So the curve with, when the rotation is in the direction of magnetic field, then there is enhancement. In the opposite direction, there is suppression. And then for 10 to minus 5, slightly faster rotation, the effect becomes even stronger. And you can imagine that for 10 to minus 3, it's even stronger and so on, but you cannot go even for faster rotation because we hit the limit of our approximation. We cannot go into the rapidly rotating system because in the very beginning, we insisted to look at the slow rotation. But you clearly see the effect. Now, it's very puzzling, of course, right? So why the effect of rotation is so small if the values of this omega are so small compared to the values of magnetic field, right? The reason why the effect is large is because what you should compare is not the magnetic field and the omega by themselves, but the synchrotron frequency omega b and omega and the angular velocity of rotation, right? So the synchrotron frequency is inversely proportional to the energy of the particle. So as E increases, this omega b decreases. So sooner or later, it becomes comparable to this angular velocity of rotation. And this is why the effect is so strong. So answering the question about the neutron star, we might think about the situation in which even though omega, the angular velocity of rotation is very small, right, but the energy is high enough that the effect may be observable. So some of the particles in the star might be feeling emitting radiation that is sensitive to the rotation. So this is something that we need to look at in more detail. So this figure shows the effect of the magnetic field strengths. We compare here the stronger and weaker fields. So stronger field is with the black stars, right? I mean, weaker field is the black stars, and therefore the effect of rotation is stronger, as expected. And the opposite, if you have a stronger field. The stronger the field, the smaller the effect of rotation, of course. Okay. So let me explain you, very quickly why do we expect that there is enhancement when the magnetic field points in the same direction of the omega. Well, this is what is shown here is the effects of the rotation force and effect of the Lorentz force on the rotation. If omega is positive, meaning that the rotation is counterclockwise, right? Then if the omega is negative, then rotation is in the opposite direction, clockwise. Now, under the Lorentz force, if you take a particle QB positive, then opposite happens, right? The rotation is clockwise if QB is positive, and counterclockwise if it's negative. So let's take positive QB in both cases, but let's flip the direction of the rotation. If you look at this, compare these two figures, suppose you now rotate with this particle. I want to see what is the effect of rotation on this particle. I'm sitting on this particle, rotating counterclockwise, and I would like to measure the magnetic field. How do you measure the magnetic field? I look at the angular velocity of rotation, but the rotation in magnetic field is in the opposite direction. So from the point of view of an observer sitting on this particle here, the omega b, the synchrotron frequency, will be larger, just because they rotate towards each other, and therefore this observer here will perceive the magnetic field as stronger, and therefore the radiation will be stronger. And the opposite true in this situation. Okay, and this is the qualitative picture for why there is enhancement or suppression. Okay, now if you look at very large energies, and this is a recent computation of one of my students, if you look at the very large energies, you see something dramatic happening, that the ratio rapidly decreases. And it seems very counterintuitive, because it looks like the intensity itself vanishes, not the ratio, but the intensity itself vanishes. It's very strange and it's difficult to explain why would the intensity of radiation vanish, because right, the intensity usually increases with energy. So it turns out, I don't have time to go into much detail, but it turns out that we hit actually the limits of the white cylinder. Okay, so this number n and a, remember, in order to apply the approximation of slow rotation, these numbers n and a must be small enough. And it turns out on this figure, for example, when you increase energy already at this region, we already hit the limit where we cannot apply this slow rotation approximation, but rather we need to go into the full, we need to take into account the boundary of the rotating plasma. Okay, so this is in a nutshell. Let me summarize this part, and I'll see a few more minutes I'll spend about the fast rotation. So I showed you that the effect of rotation is large, and this depends on the direction of rotation. So the direction, the relative direction of the rotation and the magnetic field matters. It either enhances or suppresses the radiation. And if you want to study very rapid rotation, then you need to take into account the boundary. And I want to apply it to explain eventually the puzzle of the soft photons at the heavy ion collisions. There are some things that I don't have time to now discuss, but let me go. Okay, I apologize, but let me go to the rapid rotation, and I'll say a few words about that. And if you have questions, then maybe I'll go back and answer them. So, how do you take into account the fast rotation? We don't want any particles, of course, to cross the light cylinder. Nothing can rotate faster than the speed of light. So what do? Well, what we've done, we said, let's impose the MIT boundary condition, right? MIT boundary condition tells you that the radial current on the surface of this light cylinder must be zero. That guarantees that no momentum, energy, or angular momentum crosses into the forbidden region. Now, naively, you would say, why is it so complicated? Maybe we should simply tell that the wave function itself, right, the solution to the Dirac equation, must vanish at the light cylinder. It turns out that this is not possible to do. It's impossible. And this is the whole idea of the MIT boundary condition, is to force the current to vanish, the radial component of the current to vanish at the boundary rather than the function itself, which is impossible to do. And this condition is equivalent to the condition that this radial Dirac gamma function, so this the condition that the psi, the solution to the Dirac equation on the boundary, be an eigenfunction to the radial gamma function. And it's easy problem to solve. It's linear algebra after all. You can solve this problem, but this is the easiest problem to solve. And then you need, because when you need to now find the spectrum of the problem, it turns out that it's a very complicated problem. If you remember when we discussed at the very beginning the solution to the Dirac equation, we said when you take the wave functions to infinity, you require that it vanishes there, and this produced that required that the wave function be polynomials. Okay, now we don't have this requirement. We don't take the wave function to infinity. We impose a boundary condition at a finite distance. Okay, and therefore this quantum numbers, the principal quantum number, is not an integer anymore, but rather a real number. So this lambda, that is the principal quantum number, is integer only if you take the boundary to infinity. Okay, so this is the main effect. So instead of integer quantum numbers, you have real quantum numbers, and it presents a lot of difficulties. Now we still didn't overcome all the difficulties, but we applied this now the solutions which we found for the fast rotation to compute the current in the presence of the boundary at some finite distance r at a final value of the axial chemical potential. So suppose you have a plasma in a cylinder, no rotation, right? You can add rotation if you say that r is 1 over omega. Okay, but even though no rotation, just boundary, and you say, let us compute now what is the current that is induced by magnetic field in its own direction at the presence of the Kirill anomaly, right? We know that it's called the Kirill magnetic effect, but we want to know what is the effect of the boundary. And we found that the effect of boundary is pretty dramatic. First of all, unlike without boundary, where only the lowest Landau level contributes to this effects, at finite r, all Landau levels contribute to the CME current, all of them. Okay. We also found that the Kirill magnetic effect increases with magnetic field. So this one here is the Kirill magnetic effect in vacuum. I mean, not a vacuum, but without boundaries. I'm sorry. Okay, it's 1. It's normalized to 1. If you have a very tight boundary, so if r is very small over here, then there is no Kirill magnetic effect at all. Okay, so when you increase the r, the boundary becomes, the size of the cylinder larger and larger. The radius is larger and larger. You slowly approach the normal Kirill magnetic effect here. Okay, and this is, well, this previous plot is along the center of the cylinder, but we also can study how this current depends on the distance from the center of the cylinder. You can see it starts from 1 and drops to 0 right at the boundary of the cylinder. Okay, now our program now, what we want to do is to compute this Kirill magnetic effects, and the computation is almost done, and we're intending to publish it very soon, and then switch to this our main problem of the synchrotron radiation by rapidly rotating systems, and see how can we take into account this effect of finite boundary, rotating boundary on the spectrum. Okay, to summarize, we computed the synchrotron radiation at finite b and omega. We've seen how this influences the spectrum. We've done this calculation for slow rotation, but now we want to do fast rotation because it's very interesting for heavy ion collisions, for low energy heavy ion collisions. And as byproduct of this, we were able to compute the chiral magnetic effect and seen how the finite boundary of this system affects the value of the anomaly coefficient. Thank you.
Thank you. Thank you, Kirill. Can you hear me?
Yes, I can hear you.
Yeah, no, thank you very much. It's a very nice seminar. So we already have a raised hand.
Good.
Giorgio, please.
Hi. Thanks for a very nice talk. Just as there is something called, just to ask, there is a famous effect in rotating electrons called the Sokolov-Ternov effect.
Yes.
Which is sort of related to the Unruh effect, but the bottom line is that electrons, or in your case, I guess the quarks of the quark-gluon plasma, polarize themselves.
Right.
Have you looked at this? I mean, polarization was also seen in
yes.
hadron collision.
Yes. So first of all, hi, Giorgio. Yeah, we looked at this effect, and I actually have some results which I didn't include in this talk. Definitely first of all, of course, we do see the polarization of the fermions due to the radiation of photons. The whole effect happens because the rotation intensity depends on the polarization of the fermions, and therefore as you emit more and more photons, the difference between the numbers of the up and down polarizations increases, and this is what is called the so-called Ternov effect. We do see that, and we do see the dependence on the angular velocity, but I cannot recall which direction it goes. But we do have these results, which we kind of summarizing right now into the pretty big paper with all these results. So to answer this question, yes, there is effect. We see it.
Okay, Christian.
Okay, thank you for the nice talk. Very interesting applications, I think. I have a question. The system you're describing is rigidly rotating, isn't it?
Yes.
Yeah. Okay. For example, in a plasma, it's supposed that you have positive charges, negative charges are also rotating on the same direction.
Yes.
So the emission of photons will be, in principle, you can average between positive and negative particles.
Right.
So this is not some kind of cancellation of the effect.
Okay, thank you for this question. Let's look at this like this. Suppose we have two kinds of particles, positive and negatively charged in plasma, right? You apply a magnetic field and rotate them, and as you correctly said, some of them will rotate in the same direction as the magnetic field pushing them, and some of them will rotate opposite direction, and the effect may cancel out. Actually, it doesn't cancel out, and the reason is following. Suppose those particles for which the radiation is suppressed so much that we can neglect them, and for those particles that the intensity is enhanced very much by some big factor, right? So half of the particles in the plasma will radiate a lot of energy. So just to give you some example, for example, let's suppose that positively charged particles will have the intensity enhanced by factor of 10, and negatively charged particles suppressed by factor of 10. Right? The total intensity will be enhanced by factor of 10 divided by 2, because only half of the particles will emit 10 times more energy. So overall effect will be enhancement of the electromagnetic radiation.
Okay, I see. Can I ask another question?
Sure.
Yeah. You mentioned the n number, n-causality. This number is some kind of limit imposed to preserve causality. It's a natural number. Must belong to naturals or what?
Yes. So what we say that we said like that. We want to study slow rotation, meaning that the system size, which is determined by the strength of the magnetic field, is much smaller than 1 over omega. So in this case, if you compute the wave function of the system, the wave function of the fermions, they will be exponentially decreasing towards the boundary 1 over omega, right? So in this region where the function is exponentially small, the wave functions are exponentially small, we simply neglect them. We say, we don't want to take this part of the space into account and neglect that what happens at the boundary of the system. Now, this is true only if this principal quantum number and the radial quantum number are smaller than that big number that you mentioned, which is in practice maybe 1,000, maybe millions, depending on the particular situation. As long as the numbers are smaller than that, those numbers that contribute to the intensity of the radiation, our approximation is consistent. As long as we start to approaching to those big numbers, then what happens is that we become sensitive to the boundary of the system, which we don't take into account in a proper way, right? So in order to take this in account in the proper way, we need to impose some kind of boundary condition, make sure that nothing goes and rotates with forbidden angular velocity. But if you want to stay away from that, then the quantum number should be small enough.
And in the other case, with the MIT conditions, this is not necessary.
Right. So, and then we said, we don't like this artificial limit, right? Because we impose this limit just to make sure that we can do the calculation. And then we say, we want to study rapidly rotating systems. This is interesting. And to be able to do that, you need to impose boundary conditions. That if with the proper boundary conditions, you don't need to impose any extra requirements on the numbers n and a. Okay, so now you can compute the intensity of radiation for any energy, for anything that you want. The only problem is that the computation is tremendously complicated, because now everything is connected. You cannot solve this problem step by step. For example, the principal quantum number itself is dependent on the angular velocity of rotation. Right, so it becomes a very complicated nonlinear system that takes time to actually solve.
Okay. Thank you very much.
Are there more questions? I have a couple of questions. So just continuing the discussion from Christian, there is this procedure that Igor Shovkovi applied when you want the wave the current to vanish outside the surface, which is to make the mass of the wave function infinity outside it, and so it's not. The wave function is not zero, but it cannot propagate. Is it something you can apply there?
Yes. Actually, this is another option we're considering. Quite frankly speaking, we do not know which of these methods will produce the correct answer. We don't know the correct answer, but right. So it's a very interesting problem, and we'll try. Well, yes, we'll try to do this as well, because we think we understand.
You don't necessarily need the wave function to vanish. It's enough that it doesn't propagate. That's my question.
Right.
Yeah.
But you see, you don't want to lose doing this. So I'll kind of go one step further. Doing this, you don't want to lose the effect that the wave function in principle can be outside of the white cylinder. There is no contradiction in principle of the wave function being there. Like Giorgio mentioned, the Unruh effect, right? Just because the particle accelerates, right, it doesn't mean that you have to cut the wave function off. It just becomes the space-time is split into now regions in which in some of them you cannot observe the wave function in the other region, right? Right. So this is this kind of effect. In principle, you can let the wave function be outside of the white cylinder, and in fact, the MIT boundary condition does just that. The wave function is non-zero there, but the current is zero. It's a little strange kind of thing, but the question is how to correctly take this into account is open. I don't think that in the literature there is a definite solution to this. And yes, to answer the question, we're thinking about this problem. We're thinking about making the mass infinite to suppress the propagation of particles there.
Okay, and just a last question, and I think this is very quick. It's just because I don't know. I mean, the quark-gluon plasma, the rotation of the quark-gluon plasma is not homogeneous, as Christian pointed out. But how does it evolve in time? I mean, does it change a lot before the plasma hadronizes, or is it more or less constant in time, or can it affect this relation between rotation and magnetic field, or is it more because magnetic field goes down very quickly, but how is it rotation, and how this relation between both evolve with time?
Yes, that's it's a very good question. Right, so it changes. You can see here, right? It changes with energy, and it changes with time as well. And it's also, I don't have there's many plots. Maybe actually down there. Oh, here it is. There's a distribution of this vorticity in space, right? In perpendicular plane. You can see also a variation from deep red, 0.15, right, to like yellowish. Like it's factor of 2. You can see the change between the different areas in space, and the same in time. It changes. So and magnetic field is changing too. So the only what we need to make sure that this change is slower than the typical. So for magnetic field, you can think of that the typical time it takes to say rotate to emit a photon is 1 over omega synchrotron frequency, right? So the magnetic field should change slower than this characteristic time. Then you can apply these approximations that magnetic field is constant and the same for omega, or the angular velocity.
Yeah, but then you can also apply this condition that the rotation is approximately constant.
Yes.
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 Okay,
so everything changes in time. Everything. But whether it's a quick change or slow, you should be careful with about that. I did previous calculations for the plasma radiation in magnetic field, and there, this approximation of slow change in magnetic field is pretty good actually. So if you go this here, so this curve, even though it looks like a rapid change, it is kind of a couple of orders of magnitude change. It's still slow enough compared to the scales in plasma.
Yeah, sure. Okay. So more questions? If not, let's thank Kirill again virtually.
Yeah,
I will stop the recording now.
Yeah, and if you have questions, follow-up questions, you can always shoot me email, and I'll try to answer.